A rational function has the form f of x equals p of x over q of x, where this is a polynomial and so is the denominator. So anytime you take two polynomials and put them as a quotient, you're going to get a rational function. For example, f of x equals 2 over x minus 2 is a rational function. Monomial over binomial. G of x is another example. Monomial over binomial. Or we have h of x, another one, binomial over binomial. I could have a binomial over a trinomial. It doesn't matter what type of polynomial it is. As long as you're looking at a quotient of the two, you're going to get a rational function. First task is to evaluate a rational function. As before, we input the given x, or whatever you want to call the variable, and we get an output of y. For example, if I take the above function f of x equals 2 over x minus 2, and I say evaluate f of 3, for example, that means here's the input. I'm going to take the 3 and go put it in all the x's, and the output is going to be 3 minus 2 is a 1, which is 2. That's my output, or my y value. So in ordered pair form, on the graph you would see the ordered pair input 2 and output, or I'm sorry, input 3 and output 2. So that's just a side note, but the evaluation is done just as before, like other functions. For example, p of t is t minus 2 over t squared plus 5, and we're supposed to evaluate p of negative 2. So again, that's the input. We're going to put negative 2 in all the locations where we see the t. So right here and right here, we're going to replace it with negative 2. So I have negative 2 minus 2 all over negative 2 quantity squared plus 5, which is going to give me a negative 4 upstairs, and that's going to be a positive 4. 4 plus 5 is 9 downstairs, so there's my output. P of negative 2 is equal to negative 4/9. The domain of rational functions, that's the second task, as before, involve all the quote-unquote good x values. In other words, all the x values that give me a reasonable output y value is going to be the domain of that rational function. For example, let's say I have a function f of x equals 2 over x minus 3, and I want to find the domain of it. So in other words, all the good x values. All the good x values that give an actual defined output. So since this has a denominator, and all rational functions will have a denominator, we want to make sure that the denominator cannot become 0, because we know when a denominator becomes 0, the expression becomes undefined. So you kind of think backwards and you think, when will this be 0? You pull it out and you say, well, if x minus 3 is 0, x equals 3 is a bad value. Because if I put it in, I'm going to get, let's say, f of 3, if I test it, f of 3 is 2 over 3 minus 3, and I get 2 over 0, which is undefined. So it didn't give me a good output back out, which means 3 is a bad value. Everything else is okay. All other x's are okay. You give it any input a value of x, it's going to give you a reasonable output. This is the only place that the denominator becomes 0. So for the domain, in set notation, we would say all x such that everything is okay except we're going to exclude x equals 3. So all okay except x equals 3 would be, in set notation, toss out x equals 3, keep everything else. Same question, find the domain of g of x. Well, again, g of x has a denominator, and my goal is to make sure this denominator doesn't become 0. So I say, what if it becomes equal to 0, and then I solve that little mini equation, and when I get this value, this is a bad value. So I have to exclude it. Again, if I want to test it, I can go ahead and test it out. You don't have to do it each time, but if I input negative 5, notice we already know we're going to get a 0 in the denominator, which is going to be undefined. So we say for the domain, everything is okay except that guy that makes the denominator 0. All x such that x cannot be -5. So there was only one bad value to exclude. All other x values you input, you're going to get a good output. Find the domain of this function. Well, again, same idea. I take this guy and I say, what if it were to become equal to 0? Things would go bad. And this is actually a quadratic equation, so I can factor that, x plus 2, x minus 2, and there's going to be two bad values that are going to pop out. So two bad values must be excluded. So both bad values, if I want to quickly test them, if I test the x value of 2, I put it in, I get 6 minus 2, which is 4 upstairs. 2 squared is 4, 4 minus 4 is 0, so that's no good, it's undefined. If I test the x value -2 that I found here, I put it in, I get -6 minus 2, which is -8, and then -2 squared is again 4, 4 minus 4 is 0, which is undefined. So both are bad x values, and the domain is all x such that x cannot equal -2 or 2, and everything else is okay. Now let's say I take something similar to this guy where the denominator was x minus 4 and I change it to x plus 4 and I want to find the domain. Well, again, I go downstairs to the denominator, I set it equal to 0, and I say what if it were to become equal to 0, and notice this polynomial is prime and you can't factor it. And also, no matter what you input in here, it's always going to be some number plus 4, so it's never going to be 0. No matter what you do, you're not going to be able to find a number such that when you add it to 4 in the real number system for it to go away and become 0. Anything I put in gets squared and then gets added to the 4 and gives me something even bigger than 4. Even if I put a 0, I get 0 squared plus 4, which is still a 4. So since the denominator never becomes 0, there are no bad values, which means everything is good and the domain is all x's work. X such that x is all real numbers. So again, I wasn't able to solve the quadratic equation and pop out my solutions by factoring. And if I analyzed it also, there's no way the denominator becomes 0 ever, so the domain is all real numbers. Every single input I give it will give me a good output back out. So next task, let's evaluate functions, which was the first thing we did, and also find domains graphically. So both things that we did by looking at it in algebraic form, we're also going to look at it graphically. Okay, so we've got use the graph to evaluate each expression, give the equation of the vertical asymptotes. So these dashed lines are actually called vertical asymptotes. They're sort of like borders where you can't cross, and the graph gets closer and closer to them, but it never touches them. So let's just go and do the evaluation part first, because give the equation of vertical asymptotes is really related to the domain. So I'm going to go to the input -3. Remember, that's the x value. So f of -3 says the input, or the x, is -3. So I'm going to go to the x value of -3, and then I'm going to walk over to my graph, and there is the ordered pair, -3, the y value happens to be 2, so the output is 2 for the first one. Next one says f of 1, so let's go to f of 1. In other words, the input, or the x value, is 1. And when I'm at 1, my graph goes through 1, so I am not really moving, I'm not going up or down, which means 1, 0 goes through my graph, or my graph goes through that ordered pair, so the corresponding y value for the x value 0 is 1. It's the same way we evaluated functions graphically before. Let's go to the next graph. Again, the input is -3, so I go to the x value -3, and I go up to my graph, and that ordered pair is -3, 1. So the y coordinate that I pull out is a 1. Then I go to f of 2. The input is x, so I go to the x value of 2, and notice there's a border there. for vertical asymptote. And that means it's undefined. So basically what's happening is sort of like you're getting a 0 in the background, you're getting a 0 in the denominator, and you're getting a vertical asymptote. It's becoming undefined, kind of like way up here when we were looking at bad values. Whatever bad values you get, they give you undefined terms. You don't have an actual ordered pair that comes out of it, and that corresponds to what's happening here. When I go to do f of 2, the x-coordinate 2 doesn't give me anything other than this dashed line, which is actually not part of the graph. Only the blue stuff is really my graph, not the dashed line. You'll see rational functions graph into things that have different branches and things that may have asymptotes. Now let's go back to the second idea, which says, what are the domains? Well, for the domains, it's basically, for the first one, all x such that, remember, everything is good. On this side of the border or the dashed line, I have a graph. On the other side of the border or the dashed line, I have a graph. And this graph occurs exactly at -1, so all x are okay except -1. X equals -1 is not part of my domain. Similarly, for the second one, all x such that everything is okay. All of this contains a curve to the left. All of that contains a curve to the right. This dashed line, which is an x value of 2, is no good. This is my vertical asymptote, so x cannot equal to 2 is my domain. Everything is good except 2. Now, equations of vertical asymptotes, which is what the problem asks for, I'll call them VA for vertical asymptotes. The equation of the vertical asymptote, well, for the first one, it's just this vertical line going through -1, so x equals -1 is the vertical line equation. Part B, it's a vertical line going through 2, so x equals 2 is the vertical line equation. So if it just says give the equations, all you're doing is you're putting x equals the dashed line, whatever it goes through, and x equals that dashed line, whatever it goes through. But if it says what's the domain, then you got to exclude those values, because on those dashed lines you don't have a graph. You only have a graph before it and after it. Okay, remember function notation. Given these two functions, evaluate first f plus g of 3. Well, the 3 applies, it's an input for both. So I'm looking at f of 3 and also g of 3, and then when I'm done, I basically add those two values. We've done this before, so f of 3, I go to the f function, is f times 3, which is a 15 output. G of 3, I go into the g function over here, and I get 3 plus 1, which is an output of 4. And then I just add those two, and I get 19. So f plus g of 3 is equal to 19. Similarly, now I'm dividing the two functions. So both get the input of 0. I get f of 0, then divided by g of 0. Basically, input the 0 into one function, input the 0 in the other function, then divide the corresponding values. So I'm just going to look at them as top and bottom. If I put a 0 in my f function, I get 5 times 0, which is just a 0. If I put a 0 in my g function, I get right here, put in a 0. So I'm going to put the 0 in, that's 0 plus 1, which is just a 1. And remember, 0 divided by 1 is just 0. So f over g of 0 is going to give me an output of 0 again. So when you're analyzing function notation, don't let it confuse you. Just give it the input and then analyze the outputs and apply the operation indicated. If the f and g were stuck with maybe no other operation between them, that would be a multiplying, and I would give it the 3, and I would give it the 3, then I would multiply the results. Or if it was a minus, I would subtract them.